So, hello everybody. Now upcoming we have the Miniac project, which is about data acquisition, FPGA based, and using the power of RISC-V in that case, which will be presented by and is developed by Nikola and Minela. Give them a warm round of applause. Go ahead.
Hi everyone, and welcome to our presentation. My name is Nikola and my colleague is Minela. We will present our project, the Miniac, a RISC-V based diagnostics tool. So to start off, I would like to give a quick background of why we developed the Miniac. Right now, me and Minela work with a team called Chili Chips. We come from Sarajevo. We consist of a small team of about 10 engineers that work usually on FPGA and embedded systems. Right now, we are working on a project called Uberclock. Uberclock is a project where we want to develop a board that will give out a consistent and precise clock comparable to that of a Stratum 5 atomic clock. That's the idea anyway. This project is also funded by the NLNet Foundation, so we would like to take this opportunity to give them a big thanks for their cooperation, past and present. Now, what is the goal of the Miniac? Our colleagues that work on the Uberclock project reached out to us and told us that they had a little problem. While working on FPGA-based projects, they had actually no idea what was happening on the FPGA while working with signals, such as when they needed to sample an atomic clock. So they needed a little tool that would help them visualize and give them a better sense of what was going on in the FPGA and what those signals looked like. We tried out a couple of tools that were already available, all open source. Unfortunately, we didn't have much luck using those tools, so we decided to develop our very own tools. And in the end, that proved to be a better route for us because we had complete control over what we were doing and we had a better sense of how everything worked. So the idea of the Miniac is to snoop around over the FPGA, see what the ADC is sampling, then send it via UART to our laptop, for example. There we visualize the samples, recreate the signal from the samples, and plot out the frequency spectrum to see what frequencies we're actually dealing with. This is the architecture of our Miniac. As you can see, we actually enumerated the couple of steps, so I'll run you all through it. First of all, we have the ADC. The ADC, as you all know, is responsible to sample signals. I'll show you later a picture of the entire system, how it all looks connected and everything. So the ADC samples the signal, sends it via IDDR and ODDR. IDDR and ODDR are a double sample rate blocks, I'll call it. The IDDR, for example, samples an input signal on the rising and the falling edge. So, example, we are filling two registers at the same time with data, one being sampled at the rising edge, the other one being sampled at the falling edge. And we have the ODDR that is responsible for taking both registers and then packing them in a series, and then sending it to the CSR, the control and status registers. Now, from the CSR, we actually have two paths. We can send the data directly via the UART controller onto our laptop, or we can send it to a RISC-V processor, which my colleague Minela will talk about a little bit later. I will focus on, in the following slides, a bit more what happens when we send it directly from CSR onto the UART bridge. This is the entire system and how the Miniac actually looks. As you can see on the right picture, we have our Xilinx RTX 7 FPGA board with a ADC and DAC special board. The ADC is the one board on the left, the DAC is the one on the right. For the Miniac, we actually do not need the DAC, we just kept it as a reference. So when we sample the signal, we like to send all the data directly onto an oscilloscope, as you can see on the picture on the left, just to have a good reference if we are doing things right. And the ADC on the left is connected to a signal generator. As you can see, it is set up to generate a sine function that will be sent and sampled by the ADC. This is all connected via UART to our laptop, as you can see on the left picture. And on the screen you can see a Python script we have written to reconstruct signals from those samples and do a fast Fourier transformation to give us a frequency spectrum of the sampled signal. So we had two approaches, as I said. The first one is the direct snooping method. The direct snooping method consists of, as you can see, the signal source. We sample it by the ADC, send it to the FPGA, and then straight to the UART bridge bypassing the RISC-V processor. From the UART bridge, then we send it to the PC where we have our little Python scripts doing their magic. As it's written here, the process is sampling by ADC, send it to the FPGA, and then have it sent directly to the UART bridge. This method has proven to be a bit slowish, as you can see from these pictures. At the start, we estimated that we could reconstruct a sine of about 960 hertz, a little bit less than a kilohertz, which is practically, I'm not going to say unusable, but something similar to that, because nothing in the real world is about less than a kilohertz. But Minela is going to talk a bit about why we had this problem specifically. I'm just going to show you the results here. So on the left side, you can see a sine of 50 hertz being sampled, reconstructed from the samples. The samples are actually marked with a red dot, and the entire signal is with the color blue. And underneath you have the frequency spectrum showing that we have actually sampled the 50 hertz signal. And on the right is actually the fastest frequency we managed to reconstruct, which it was about 120 hertz, which is a lot less than the estimated 960 hertz. Luckily, we did manage to overcome this huge problem, and my colleague Minela will talk about it next up.
Yeah, so obviously that didn't work. So what should we change? We have the CPU on the FPGA, so like why not use it? So this is like new flow chart. It's simple. There's a sampling from ADC to the FPGA. So we store the samples in DMEM, so data memory, which is internal to FPGA. We store it in so we chose a 1024 sample buffer, which is a circular buffer, so we store it in the internal memory. Then after the buffer fills up to its full size, we send that to the PC in one entire block. So yeah, this is a hardware-software co-design approach. So basically, on the first approach, we had to do the same thing 1,000 times. So this way, we reduce the sampling by just sending one big batch of data. So did it work? Yeah, these are the results. So as you can see, results are like night and day. Here we achieved the maximum clean signal that we were able to reconstruct at approximately 250 kilohertz, which is like 2,000 times better than the first approach. Yeah, so basically some takeaways from this is if you need a fast sampling, direct per sample data transfer via UART is really impractical for high frequencies. So the second takeaway is these modern FPGAs are really strong tools. So yeah, if you have one, use on-chip CPU for data buffering, because it will help you a lot. And third takeaway at the end, batch processing. It isn't really something new, but it is your best friend when dealing with slow communication interfaces. Also, the maximum speed here isn't really the problem of the UART. It is more of your DMEM resources. So we didn't have to choose 1024 samples. We could use more, but again, it all depends on the chip you have and DMEM resources. So yeah, we also, everything we did is open source and on GitHub. We encourage you to try it, reproduce it, and maybe even build on it to make something even better. You can find everything on there, VHDL code, all firmware for RISC-V CPU, also our Python scripts and everything. Also check the Chili Chips GitHub. There's a lot of open source projects that are really interesting. Yeah, so thank you. That's all from us. If you have any questions, feel free to ask.
Does the CPU you have, does it support the USB directly? Because I think you can get even bigger bandwidth, even better throughput with using like USB even 2.0, just a raw bulk access from the USB.
I'm not completely sure. It probably does, but at the moment when we were developing the Miniac, we tried a few methods. Actually, this was the best one we chose. The best one, the one that gave us the best results. We could check it out, for example, for future projects, and the idea with the Miniac or any other project we do is to make it reusable. So we will definitely reiterate this project probably sometime in the future and check out if it is possible, and if so, then maybe maximize the speed that we can actually sample. Thank you. Any more questions?
Hi guys. Actually, I'm also from Bosnia, so this is really nice to hear that someone else is doing similar stuff, or should I say interesting stuff. I'm not saying that I do interesting stuff. Good topic, good presentation. Just a question, because I'm more of an electronic nerd / guy in some works. Did you test maybe other USB to UART chips, or just, as if I saw correctly, it was just CP2102?
Right now we only did it for this one, since this is the one we're using on the concrete project. So the idea, the goal of the Miniac was to make it work for this setup. Maybe in the future we'll try something new. We never know.
Just a question from experience. I had issues with CP2102 in some other boards and projects, but with the tried and true Max FT 2032 or 232 FL, I had less issues and was more stable. So if you have limitations like it needs to be TTL to USB, CP2102 is flaky sometimes. Just my experience, and want to thank you again. Thank you.
Yeah, sure. Thank you.
Anyone? We still have plenty of time. Any more questions?
If there aren't any more questions, I encourage you all to join us or ask any more questions. Reach out to Chili Chips if you have any suggestions, further suggestions, or if you want to cooperate in future projects. We are very open to cooperation, and we brought a batch of stickers with us from Sarajevo. So if you want, they're displayed on the tables in the Maker Fair area, so feel free to come and pick up a sticker.